Hello everyone, welcome back to my YouTube channel. Today we are going to study crystallographic directions. So what are crystallographic directions? They are basically directions from one point coordinate to another point coordinate within a crystal system. So direction from one point coordinate to another within a crystal system. Okay, so how is a crystallographic direction defined? It is defined as a line or a vector between two points. Defined as a line and or a vector between two points. Now, there are certain steps that need to be followed to define a crystallographic direction. So, steps to determine crystallographic directions are okay. So, first we have to establish a coordinate system. So, a right-handed XYZ coordinate is established. And it, for convenience, it can be linked with the corner of the unit cell. Its origin should be the corner of the unit cell. Okay. Next step. Now the coordinates of the 2 points that constitute the direction, they lie on the direction vector. Okay. Sorry. So the point coordinates lying on the direction are determined. So you need to define the point coordinates that constitute the direction. Okay. Now suppose your tail components are x1, y1 and z1 and your head components are x2, y2 and z2. So how will you get the direction? Now you have to go get tail minus head. Okay. So that will sorry, you have to go to head minus tail. Sorry, this was wrong. It should be head minus tail. So it will be x2 minus x1, y2 minus y1 and z2 minus z1. Now then they are normalized by dividing by the lattice parameters. So suppose A, B and C are your lattice parameters along x, y and z respectively. So your normalized direction becomes x2 minus x1 by A, y2 minus y1 by B and z2 minus z1 by C. Okay, so you get three numbers. Now if necessary, these are divided by a common number or divided or multiplied by a common factor to get the smallest integer. Multiplied or divided by a common factor to get the smallest integer. These directions are always in the integer form and are never left in the fractional or decimal form. Now, the resulting numbers, they are enclosed in square braces and they are not separated by commas. So, this is the representation of a crystallographic direction. So, here this is your U, this is your V, and this is your W. Okay, so U can be written as n, that common factor, into x2 minus x1 by a. V will be n y2 minus y1 by b, and W will be n into z2 minus z1 by c. Okay. Okay. Now let us see one example of some directions in cubic crystals. So let us draw a cubic crystal. Okay, so a right-handed XYZ coordinate system is this X, Y, and Z, and this is your origin. Okay, so for a direction of, say, 100 direction. So this is, all the x's are 0 except x. So x is 1. So you have, this is your 100 because it has an intercept of 1 along x and 0 intercept along y and z. Okay. Now let us look at another one. So for a direction of 110, so this has an intercept of 1 along x and y axis and 0 intercept along z. So an intercept of 1 along x, so this comes here, and then you come here, and then an intercept of 1 along y, so you move here. So then your direction becomes this, and you move 0 along z, so your final direction is this one. Okay. Now for 111, this has intercept of 1 each along x, y and z, all the three axes. So you move 1 unit along x, then you move 1 unit along y and 1 unit along z, so you reach here. So join the origin to this point, you get this body diagonal. So this is your 111 direction. This was your 110 and this was your 100. So this way you get 3 different types of directions. Now let us see some common examples. So, let us go through some example problems from the book of Material Science and Engineering by William D. Callister. So, let us start with solve problem 3.7. The problem says to determine the shown directional indices. So, the shown problem is like this. So, you have a cubic crystal. Okay, with the coordinate axes as marks. This is x, this is y, and this is z. This is the origin, this is C, this is V, and this is A. Alright, so now let us check the directional indices of this direction. So let us first check what are the coordinates of different points. So this is point 1 and this is point 2. So the coordinates of point 1 are, they will be A, 0, 0, and coordinates of point 2 will be 0, sorry, this will be, yeah, on x it is 0, then it will be minus b, sorry, it will be plus b and c by 2. So now the directional indices will be taken by the formulas u is equals to n x2 minus x1 by a, v equals to n y2 minus y1 by b, and w is equals to n z2 minus z1 by c. So from this u is equals to n into x2 0 minus a by a, that is n, sorry, this will be minus n, v will be n into b minus 0 by b, this will be n, and w will be n into c by 2 minus 0 by c, this will be n by 2. So this implies for the common factor n is equals to 2, so u v w will become minus 2, 2, 1. So this direction will be 2 bar, 2, 2, 1, and enclosed in square braces. Okay, so this is your direction. This way you can calculate. Okay, so let us move to another example. Example problem 3.8. Here we need to construct direction. Construction of a specified crystallographic direction. Okay, so the specified direction is 1, 1 bar, 0. Okay, so let us first create a cubic crystal. Okay, so this will be x, this will be y, and this will be z. So since this is our origin, this is C, this is B, and this is A. Alright. So our direction is 1, 1 bar 0. So that means it has an intercept of 1 along x, minus 1 along y, and 0 along z. So if we see, then for this we can have an intercept of 1 along x. So if we move 1 unit along x, so this is x, then minus 1 along y. So this is positive y and this is negative y. So we move in this direction for 1 unit and 0 along z. So our direction would be to join this origin to this. So this will be our 1, 1 bar 0 direction. Okay, so this distance will again be b. Alright, so that was about crystallographic directions in cubic crystals. Okay, so we have certain crystallographically equivalent directions. Crystallographically equivalent directions. What is meant by these? They can be non-parallel or parallel, but the key feature is that they have same spacing of atoms along their direction. Okay, key feature is that the atomic spacings along those directions are similar. Okay, so like some crystallographically equivalent directions are 1 0 0, 1 bar 0 0, 0 1 bar 0, 0 0 1, and 0 0 1 bar. So these are then called a family of directions. They are then termed as family of directions, and then they can be written in the form like this, enclosed in angular brackets. So this represents a family of directions. Okay. Now let us see directions in hexagonal crystals. So in hexagonal systems, some equivalent crystallographic directions do not have the same set of indices. For example, 111 is equivalent to 1 bar 0 1. So to address such a situation, we use a 4-axis system that is called Miller-Brevise indices. The 3-axis system is Miller indices, but the 4-axis system is Miller-Brevise indices. So this can be represented as like this. For a hexagonal crystal, Okay. So for such a kind of hexagonal system, in a 4-axis system, the 3-axis lies in the basal plane. So suppose this is the center. So the 3 axes that lie are like this at an angle of 120 degree each. So this is A1, A2, A3, and this central axis is the Z axis. So the angle between these are 120 degree each. Okay, and this bottom plane, this plane is referred to as the basal plane. Alright, now for a 3-axis system, the indices are U, capital V, and capital W. But when changed to 4-axis system, these are small u, v, w, and t. Sorry, u, v, t, and w. Okay, so the conversion equations are u is 1 by 3 2u minus v, v is 1 by 3 2v minus u, t is minus u plus v, and w is remain unchanged. Okay. Now, using these equations, we can see that, for example, for these directions, if we go on to see one direction, so if we change to 4-index system, what does this become? So u becomes 1 by 3, 2 into 1 minus 1, so this is 1 by 3. V becomes 1 by 3, 2 into 1 minus 1, 1 by 3 again. T is minus 1 by 3 plus 1 by 3, that is minus 2 by 3, and W remains as it is, that is 1. So the 4-index system is, if we multiply by a common factor of 3, so it becomes 1, 1, 2 bar, and 3. And for 1 bar, 0, 1, if we convert this to a 4-axis system, then u is 1 by 3, 2 into minus 1 minus 0, that is minus 2 by 3. V is 1 by 3, 2 into 0 minus minus 1, that is plus 1 by 3. T is minus of minus 2 by 3 plus 1 by 3, that is plus 1 by 3, and W is 1. So for a 4-axis system, if we multiply by 3, this becomes 2 bar 1, 1, 3. So now you can see these have the same indices, and they can be easily represented as crystallographically equivalent directions. So this is the advantage of using a 4-axis Miller-Brevise indices system. Okay. Now let us see how to uh, construct directional indices within hexagonal crystals. Okay, so going on to solved example problem 3.9 from the same book. Okay, now to draw the direction, suppose you have to draw 1, 1, 1. we can consider single unit cell and a 3-axis system. So, for a hexagonal crystal like this, okay, so this is our hexagonal crystal, and if we draw the axis, 3-axis single unit cell is a 120-degree prism. So this is A2, A1 and Z-axis. Okay, so now we have an intercept of 1, 1, 1 each on the 3-axis. So if we go like 1 on A, 1 along A2 and then 1 along Z, we reach a point here. So now if we go from origin to this point, then this direction will be like this. So this is 1, 1, 1 direction. Now how to plot it in 4-axis system. So here we have considered just a single unit cell. So this is one rhombic unit cell. This is one rhombic unit cell that we have considered here. Okay. Hexagonal crystals are always made up of 3 unit cells of a rhombus. So 1, 1, 1 was 1, 1, 2 bar 3 in the 4-axis system as derived above. So now if I draw a hexagonal crystal, I am drawing this a bit bigger. Okay, so this is the hexagonal crystal. Now, if I draw a net on the bottom surface, okay, so this is your net kind of a thing. Okay, I'll probably use a lighter shade of black. So I'll use this shade. So this is basically your net. Okay, so this is your A2 axis. This is your A1 axis. Then using multiple parallel lines. So one, two. Okay. So okay, this is your origin. Now and sorry, this is my z-axis. This is A1. This is A2. This is A3. Right. Okay. And similarly, I divide the z also into 3 parts. So this will be M and N. So now, when I have these indices, let me divide by the highest fact. Yeah, okay. Now, I move across these nets. So, 1 unit along A1, so I come here, and 1 unit along A2, so it is here, parallel to A2, minus 2 in A3, so 1, 2 in the opposite direction to A3, and then 3 units in the Z. This is 3. So I reach a point here. So similarly, what I get is the direction that is here. So if you see, we have reached up to the same direction using both three index system. This is three axis system, and this is a four axis system. Okay, so these this has also established the equivalence between these two directions. All right. Okay. Now let us check out the last solved example of hexagonal crystals. Okay, so example problem 3.10. So this is relevant to determination of directional indices for a hexagonal unit cell. Okay. So to determine the given directional indices, we first find the indices corresponding to the three axis system, and then we convert three axis system to four axis and find the Miller-Bravais indices. Okay, so first three indices or the Miller indices, and then we go on to find the Miller-Bravais indices. So for the given direction as such, sorry, so this is our hexagonal unit cell. Okay, now suppose we have a direction that is given by, so first draw the axis. This is Z, this is A2, this is your A1. Okay, so this is your unit cell. So this is bit of a distorted kind of a rhombic prism, but assume it to be a regular one. Okay, now the direction is given by this. So it is here. So this is your direction for which you have to find the indices. So let us find the coordinates of the 2 points as we had done for cubic crystals. This is 1, this is 2. So coordinates of point 1, they are 0, 0, 0, and coordinates of point 2, they are 0, minus a and c by 2. So for u we have n x2 minus x1 by a, v is n y2 minus y1 by a, and w is n z2 minus z1 by c. So we get this is n into 0 by a, so this is 0, this is n into minus a minus 0 by a, so this is minus n is equal, and this we get n into c by 2 minus 0 by c, so n by 2. So we have to keep n equal to 2. We get UVW as 0, 2 bar, 1. Okay. Now let us convert this to 4-axis system. So for that we have small u 1 by 3 2u minus v, that is 1 by 3 2 into 0 minus 2. So this is 2 by 3. V is 1 by 3 2v minus u. So 1 by 3 2 into minus 2 minus 0, that is minus 4 by 3. P is minus u plus v, that is minus 2 by 3 minus 4 by 3, that is plus 2 by 3, and then w is equals to w, that is 1. So in 4-axis system this becomes, if you multiply by 3, so 2 4 bar 2 3. Okay, so these are the indices in 2 different systems. Thank you. In next lectures, we'll see how to find and define different crystallographic planes.